dearest one. I know you've been following us through concept of motion and conservatives. Now we introduce the third book of physics called waves. Waves treats matter as disturbance. So we'll say that waves are disturbance originating from a vibrating body, and they propagate from one point to another, transferring energy through the path of their propagation. For example, if I hit this here, you are hearing the sound, aren't you? Now you are hearing the sound, but it's not as if your ear is on this board, no. But when I hit it, what happens? It's a disturbance. There is a vibration which creates a disturbance which can propagate from here even to your audibility now that you are hearing it. And it transfers energy as it's moving. And what is the transferring of energy, or the energy we are hearing now? Sound energy. So from there we can define wave as a disturbance which originates from a vibrating body, which can be transferred or propagate from one point to another, transferring energy through its path of propagation. I know you may be wondering why I'm using the language propagation. Can't I use transportation? Listen, many a times we misplace these things. Somebody will tell you, and I propagated from one but not to that, or no, a human being cannot propagate. Propagation simply means you are here, you are here, you are here, you are here. Just along the whole way you are found there, and that is how wave moves. But transportation means a complete movement from one place to another, just the way we treated on motion. So we talk about the types of waves. There are two basic types of waves. Most especially those of you who are writing GCE and WAEC, you are the one that will take the written part of this. They will always say, state two types of waves. The major thing you have to tell them: one, we have the mechanical wave, and the second one, we have electromagnetic wave. For the first one, mechanical wave, whenever a wave needs a material medium, listen to me, I did not say medium, I said material medium. What do I mean by material medium? A particulate medium, a medium that has particle. It may be solid, it may be liquid, it may be gaseous, it may even be plasma. But as long as that it has particle, we say it's a particulate medium. Any wave that needs a material medium for its propagation, we said is an example of mechanical wave. Example: sound, water wave. All these ones, they need material medium for their propagation. If there is no air, you will notice that I will be opening my mouth and closing it, speaking, shouting, but you will not hear me. But because there is air in this environment, you are able to hear me. Why? Because sound needs what? Material medium for its propagation. While electromagnetic waves are those waves that need no material medium. Whether there is a material medium or not, they will propagate. Example: the light, infrared, gamma ray. There are many. But I always tell my students, for remembrance, remember this: Gaksule. Gaksule for electromagnetic waves. These will help you to remember all electromagnetic waves. The first one there, Ga, reminds you of what? Gamma ray. X remains X-ray. U, ultraviolet ray. Light, that is L. And we have what? Infrared ray and radio wave. These are two basic types of waves. Waves can also be categorized or classified in another group, which we call longitudinal and transverse. It either will have longitudinal wave or transverse wave. A wave is said to be longitudinal when the wave is moving in the same direction or parallel to the vibration causing it. Example: if I have a spiral spring just here, and I pull the spiral spring and let it oscillate, what do you see? It goes up and down. And as the spring is going up and down, the wave is creating is also going up and down. We'll say that that is what? Longitudinal. The sound you are hearing from me is reaching you as a result of compression and ray fractions of air columns that I've created is also what? Longitudinal. While transverse is obtained when the wave is moving perpendicular to the vibration producing it. Example, if I have a guitar on my hand and I'm plucking the guitar, my hand is going up and down while the wave on the string of the guitar is going this way. That means it is perpendicular to the source producing it. We'll say that that is transverse. Water wave. If I throw this marker into a bucket of water, you see the marker going up and down, which is the source producing the wave, while the water wave itself will be going this way. We'll say that it is perpendicular to the source producing it. That is also what? Transverse wave. First one, take a proper look at this diagram. Don't miss it. Take a proper look at the diagram. First, you see here that we labeled A. Secondly, I can label all the points I have here as A, B, C, D, E, F, G, and H. This point labeled A, you can see that from the rest position to the maximum height, that is what we have. And it's called the amplitude. So we'll say that the amplitude is the highest vertical attainable displacement by any particle in wave. Now, from there, from this point to this point, we have a complete toe. Just like my hand moves this way. It's a complete toe. But it must come back to where it's starting from to become what? A wave. Because we said it must be a complete toe and fro. Now it gets back to this point. This is a complete fro. Here is a complete toe. So from this point, watch my hand. From this point to this particular point, all this is what we call one cycle. So when you talk about one cycle in a wave, it must be like this. So that here is positive and here is negative. That is to and fro. Some people will just choose here and tell you that it's a cycle. No, this is half cycle, a positive cycle. And this is another half cycle, a negative cycle. When you join them together, you have one complete cycle. So as I said, amplitude is the highest vertical displacement attained by any particle in wave. One cycle is one complete to and fro movement of a particle in wave. And the time now taken to cover this one complete cycle is called our period. What did I call it? I said is period. The time taken to cover one complete cycle is period. While the total of this is your cycle. Many of us, once we see this diagram in question, we are so scared and some will do jump and pass. No. Once you see this diagram, just know how to count your cycle and that is all. For example, how many cycles do we have here? Count with me. From here to this point is one cycle. And from here to this point is another cycle. So we have two cycles here. Once you are able to count your cycle and know how to divide it with the time that have been given to you, then questions on frequency and period will not be a problem for you. So frequency, coming to frequency, you always hear of that, is the number of cycles in any given question given to you divided by the time given. Now if you bring it down to one cycle alone, we'll say that frequency simply means what? One cycle all over period. That is frequency equal to 1 over capital letter T. Now you see where I put lambda. Lambda here simply means wavelength. What distance can that wave cover in a given cycle? You can see places that I labeled for wavelengths. This is the peak, just like a hill. And in physics we call it the crest. While here, which is like the valley, we call it the trough. So whenever we'll have from a peak here, which is the crest, to another successive crest. Please, I did not say from a crest to a crest, because if I extend this here, I will have another crest. So you can't mark this from here to here and tell me that it's wavelength. No. We talk about successive. That means after this crest, the next one that is coming to it, From this one to that one, we have what we call wavelength. Also in trough, after this trough, the next successive trough, the difference between them is also a wavelength. Then the last one you may not regularly see in your textbook is that the difference between two particles that are in phase. B is in phase with F. How? I know that's what is running in your mind now. When you say that two particles are in phase, it simply means that those particles at the same vertical level, they will be the same and both will point in the same direction. So apart from B and F that I labeled here, can you identify other particles that are in phase? Can you do that? Look at A and E. They are in phase because A and E, they are on the same vertical level and they are pointing in the same direction. See C and G, they are in phase. D and H, they are in phase. So two particles that are in phase, the difference between them is also what? Wavelength. Now from there we'll come down to wave speed. Just as we handled in motion, we'll say that speed is the distance all over time. The same thing here. Wave speed V is equal to the distance covered by the wave all over time. I know you may be saying that is not what is in my textbook, but let's see what goes on. If I bring this down to one cycle only, let's consider only one cycle now. From here to here is half a semicircle, which is 180. And from here to here is half another semicircle, which is another 180. So the distance or the angular distance covered completely here becomes what? 360 degrees. And divided by time, the time taken for one cycle is period. And 360 degrees in radian, you know, it is 2 pi. So we have 2 pi over period. But you just told me here that frequency is 1 over period. That means that 1 over period is equal to frequency. So 1 over period here is equal to F. So I can rewrite this as 2 pi F. That is why in your textbook you see V equal to 2 pi F. And this equation holds. And we call it what? Wave speed. That brings it the end on this particular area, which I call the graphical representation of wave. But before I let you go from the topic wave, let us discuss the properties of waves. Idea. Talking about properties of waves, I want you to understand something. That there are basic characters which waves carry out. First one, reflection. If you are wondering what reflection is all about and you want to get a bit of the physical meaning, take up your tennis ball and throw it on the wall. It comes back to you. Fine. When you have a wave meeting an obstacle, there is a rebound or bouncing away from that particular obstacle. So whenever a wave is moving and encounters an obstacle, it hits on the obstacle and changes direction. Whether it's coming back to you or it's going somewhere else, we'll say that that particular property of a wave, the ability to meet an obstacle and move away from that obstacle, is called what? Reflection. The second one, we'll talk about refraction. This is the ability of a wave to change its direction when it's moving from one medium to another. For example, just imagine, let's make it in human aspect. If I now say, okay, let this place turn into 2, and this place water, and the other side air, and I say now someone run from this water into the thin air, you will notice that at the boundary here, when the person is coming out from water to the air, the speed will increase, and that will bring change in direction. And if someone is running from the air to the water, the speed will decrease, which also will bring change in direction. Now relate that to wave. Whenever a wave is moving from one medium to another, there is a change in direction as a result of change in speed, and that property is called refraction. Then the third one, diffraction. Diffraction. This is the ability of a wave to bend around an obstacle. If you have been to the stream, for those of you who have been to the villages or even in town, if you have been to the stream, you'll see some stones. When the water gets there, they will move around the stone and move its way. That ability to bend around an obstacle on the path of the wave is what we call diffraction. Now we come down to superposition. Superposition. This one you can mainly see in beach, most especially around Lagos here. If you notice, you see, if one of the ocean currents is coming out from the beach and the other one is returning, you see many a times there will be something like a clap on the air and boats will drop. That idea of an overlap, sometimes they overlap to become stronger and we have it being constructive, and sometimes they overlap and become weak and we call that what? Destructive. That ability of wave to overlap with one another is what we call superposition. Now I introduce another one that looks so much like superposition but not the same. Interference. Interference is in such a way that you see two waves moving in the same direction. This one is going this way and this one is going this way. Whenever they are in phase, they are moving in the same direction, and at a point somewhere here there is an overlap. And when the overlap comes, if they are in phase, you see they will become stronger here and we have what we call constructive interference. But if they are completely out of phase, for example something like this goes this way and this one goes this way, this is completely out of phase, you see that they will cancel one another and form a wave of zero disturbance. Just like as I said in the beaches, you see they will clap together and come down. This one is strong, this one is strong, but on coming together they will settle. That means forming a wave that is weak compared to the waves forming them. But here they form a wave that is stronger compared to the two waves forming them. This one is called constructive interference, while this one is called destructive interference. I now bring the last one, which I call polarization. This one is strictly for transverse waves. Longitudinal waves do not polarize. Put that in your mind now. Longitudinal waves do not polarize. For those of you writing JAMB, you will see a question like this. Which of the following is an exclusive property of transverse wave? And some will say exclusive. Exclusive, that means the one that transverse wave do not carry out. It's not true. Exclusive there simply means what is that particular property of wave that only transverse waves can carry out? And the answer is polarization. Note that today, that only transverse waves, example light, can carry out polarization. But longitudinal waves, such as sound, cannot be polarized.